In the previous live section, we did understand why we needed the bounce logic at the input of the manual switch. This because if, in this case, here we have the FPGA, in this point we have a behavior like this. So when we close the switch, the FPGA sees this bouncing at the input. Why? We can represent the analog threshold at the input of the FPGA. We can represent the analog signal when we close the switch as something like that. In this case, the input at the FPGA in this point will be something like this. Of course, these are the level at the input of the FPGA. So we need something to filter this behavior. In this case, we have a simulation with model sim, where when the input is less than an amount of clock cycle, we don't have any output pulse. When the input is greater than an amount of clock cycle, we have the output. So, to be more general, if Fc is the clock frequency of the FPGA, and we need to filter a pulse length of p-len second, we need to count Fc by pulse length clock cycle. For instance, if Fc is 50 MHz and we need to filter something less than 40 milliseconds, we need to count 2 million of clock cycle. In our circuits, we need to debounce the input manual switch at the input of the edge detector. Of course, we want to debounce the high level, so we need to put an inverter in front of the debouncer. The same logic is if we want to debounce a low level. So in this case, we design a circuit that have two flip-flops to avoid metastability on the input, and a counter that counts how many clock cycles we want to filter. This is an example of an entity that implements these circuits. We use a generic to define the debounce length, and then we have input clock and reset, input strobe, and output pulse, declaration of our internal signal, and then under reset, we reset all the internal state. On each rising edge of clock, we strobe the input in the two flip-flop. So we strobe on the first and the first on the second. Then, when the strobe is high, we start counting count +1 until the counter reach the debounce length. If the strobe goes low, the counter is reset. So, with this logic, we filter all the pulse less than the bounce length. When the counter reaches the bounce length, we generate an output equal to 1.